Welcome to The Explainer. Today, we're diving into a class of materials that sounds like something out of science fiction, but I promise you, it's very real. We're talking about something that could hold the key to tackling some of our planet's biggest challenges, from carbon emissions to water scarcity.
Okay, to kick things off, I want you to try and wrap your head around this number, 7,000 square meters per gram. Yeah, you heard that right. That's the amount of internal surface area that can be packed inside just a tiny gram of this stuff.
So what does that even mean? Well, picture this. You take 1 single gram of this material. That's about the weight of a paperclip, right? If you could somehow magically unfold all the surface area tucked away inside of it, you'd be able to cover 1.5 football fields. It's absolutely wild.
So what is this miracle sponge? Well, it's called a metal organic framework, or MOF for short. And what's maybe even more incredible than what it can do is where it came from. See, its story doesn't start with some grand mission to save the world. Nope, it all started with a simple, fundamental question.
All right, first up, let's really dig into what makes this material so mind-bogglingly special.
Now, how did this even happen? Let's meet the inventor and get into the totally unexpected story of how MOFs came to be.
So the story really kicks off back in the 1990s with Professor Omar Yaghi. He had this brilliant idea he called Lego chemistry. By 1999, it wasn't just an idea anymore. His team created the very first stable super porous MOF, which they named MOF 5. And that was just the beginning. Fast forward to 2012, and they create another one that just completely demolishes the world record for surface area.
But this is what's so fascinating. Yaghi wasn't setting out to solve climate change. He wasn't thinking about carbon capture. He was a scientist, totally driven by pure curiosity. He was chasing the answer to a deep intellectual question.
So, what was that question? What was the big idea he was so obsessed with? The one that ended up unlocking all these incredible, world-changing possibilities.
It all came down to this. Could you build materials by design? Could you actually take individual molecules and snap them together like Legos to create brand new, strong structures that you've designed ahead of time? He called this new field reticular chemistry.
Okay, so let's get into the nitty-gritty. How do these molecular Legos actually work? What's the basic recipe for building a MOF?
At its core, a MOF is this incredibly organized, three-dimensional structure. The best way to think about it is like a microscopic jungle gym or a crystalline scaffold. It's super orderly.
And the recipe is kind of beautiful in its simplicity. You've got two main parts. First, you have metal ions. Think of these as the joints or the Lego connector pieces. Then you add organic molecules, which act as the rods or the Lego bricks themselves. You mix them together and they basically build themselves into this amazing, pre-designed scaffold that is mostly, well, empty space.
And this is why MOFs are such a massive leap forward from older materials like activated carbon. I mean, yeah, the surface area is way bigger, but the real secret sauce, it's their tunability. You can literally design them. You can decide exactly how big the pores are going to be and what their chemical properties will be. It's like having a toolkit to build a specific trap for a specific molecule.
Okay, so we have these incredible programmable super sponges. The big question is, what are we going to do with them?
Well, the list of potential uses is huge, but right now, researchers are really focused on 3 big jobs where MOFs could be total game changers for our planet.
Job number 1, capturing carbon. Imagine using MOFs as these super selective filters at big industrial polluters like cement factories to just snatch CO2 molecules right out of their emissions. But here's the best part. Cleaning out those filters to use them again takes way less energy. We're talking 50 to 80% less than the tech we use today. That's a huge deal for making carbon capture actually work economically.
All right, number 2 is harvesting water from thin air. And get this, it was kind of an accident. Scientists just noticed that some MOFs were ridiculously good at grabbing water molecules even from super dry desert air. So now you can have devices that soak up moisture overnight and then, with just a little bit of heat from the sun, release it as pure drinkable water. We're talking a liter of water per day for every kilogram of the MOF.
And the third big job? Super efficient separation in the chemical industry. Right now, a ton of energy gets used just to separate different chemicals from each other, usually by boiling them. It's incredibly energy intensive, but with MOF-based membranes, you can do that separation with pinpoint precision, potentially slashing the energy needed to make things like plastics by up to 90%. Just think of the impact on that industry's carbon footprint. Okay, so the potential here is obviously off the charts, but You knew there was a but coming, right? What's stopping us from using these things everywhere, right now?
Well, here's the reality check. On one side, you've got this incredible promise we've been talking about, but on the other, you have some very real, very tough challenges. For one, they can be expensive to make. It's also really hard to go from making a few grams in a lab to producing tons of this stuff for industry. And we need to be sure they can survive for years in harsh, real-world conditions.
But even with those hurdles, the momentum is just undeniable. Experts are predicting that the market for MOFs is going to grow 50-fold by 2030. That's because we're right on the cusp of seeing the first big commercial uses roll out, probably around 2026.
And that brings us right back to where we started, with that idea of molecular Legos. We now have this incredible, almost infinite new toolbox to build with. The materials themselves are no longer the bottleneck. So the final question really is, we have the blueprint for a cleaner world. Are MOFs the building blocks we've been waiting for to actually make it happen?